SOHO had ushered in a new era. Scientists began to see solar storms in the detail they viewed weather on Earth.
I don't think we had any right to dream even that we would learn as much about new ways of predicting space weather events, for instance, as we did from SOHO. I would have been skeptical before the mission began if you'd asked me if I thought we were going to get any new, really fundamental insight into the heating of the corona, and I think we've done that. And I think we've also begun to learn some things about the acceleration of the solar wind. So we're kind of hitting on all the cylinders, and that's pretty impressive.
SOHO's triumph was that it provided a way to peer beneath solar storms. In the way Earth scientists have used seismology to image our planet's interior, so solar physicists devised a way of doing the same on the Sun. Helioseismometers on board SOHO tuned into the sounds of boiling hydrogen gas. From 200,000 kilometers down, bubbles of gas the size of Texas rocketed to the surface at supersonic speeds. In the vacuum of space, SOHO is deaf. Instead, the movements of millions of individual gas bubbles are converted to sounds. From the chaotic din, computers discern hidden patterns. The patterns reveal the Sun's internal architecture. At last, scientists had begun to understand what drives the solar cycle. Beneath the surface, two shells nest like Russian dolls. The inner shell of hot gas rotates like a solid ball. Within the outer shell circulate immense jet streams of electrified hydrogen. The electrically charged layers slide past each other like elements of an enormous dynamo. Somehow, they reset the Sun's powerful magnetic field every 11 years to create the solar cycle. Just when there seemed no end to SOHO's amazing discoveries, the satellite fell silent. A programming error had inadvertently turned it away from the Sun.
It was pretty serious indeed. The spacecraft was in a flat spin with the solar panels edge on to the Sun, so we were getting no electric power at all. Some of the equipment on the spacecraft, both the spacecraft subsystems themselves and the scientific instruments, were facing the Sun all the time and were too hot. Some were facing away from the Sun all the time and were too cold, and there weren't many in the middle of that Goldilocks range with a comfort zone. Plus, we literally didn't even know how we were going to regain communications with the spacecraft without any power to the spacecraft subsystems. I'd say we were in pretty deep soup.
An agonizing month passed. Controllers at Goddard Space Flight Center issued signals again and again to where they believed SOHO was drifting in space. There was no response. When all seemed lost, the team went back to basics. They beamed a high-frequency radar signal towards SOHO's last known position. Seconds later, a radio dish in California detected a faint echo, barely a billionth of a watt in strength.
There was an awful lot of sense of relief that they've actually found it, but then the questions started to be asked, is it still alive? At this stage, we knew it had been in deep freeze. We had no idea as to what the damage was. We then had to come up with a way of gradually defreezing it.
Fortunately, the solar panels hadn't remained edge-on to the Sun. SOHO's orbit gradually angled them back into the light. The electrical system sparked into life. But Soho wasn't out of trouble. Within weeks, all 3 stabilizing gyroscopes had failed. The spacecraft began to drift helplessly. From Mission Control, commands were issued for repeated firing of Soho's thrusters. But thrusters were consuming precious fuel. A crisis meeting looked for answers.
These guys across the hall have been really busting their behinds for the past several months trying to get us back our spacecraft, and
Engineers eventually devised an ingenious solution.
Decided if we have to recenter our own legs and lock our loop.
On board Soho, a system of spinning wheels and cogs was deployed.
Procedure to do a roll without any risk.
It successfully halted Soho's chaotic behavior. Not a moment too soon.
yeah, day 0.
The reason why this was so important to do this quickly, this whole last strategy has been done in just over a month, 5 weeks, was because the spacecraft was basically bleeding fuel at 10 kilos a week. That may not seem much, but when there's a limited fuel resource on board and 1,000,000 kilometres or 1,000,000 miles is a long way to take a hose pipe to top up, we had to do things quickly.
We claim.
From normal?
The international control team waited nearly 7 months before Soho's cameras came back online.
Let's take a look at it. Looks like the sun to me.
Nice picture.
The rescue was just in time to follow the sun into the climax of a solar cycle, and for Soho to gain a partner. In Northern California, a new mission was conceived. Its assignment was to discover how wild storms in the sun's outer atmosphere could be driven by magnetic activity deep within. A smaller, more economical sun-watching spacecraft was designed. In April 1998, TRACE was launched from midair. TRACE's new ultraviolet telescopes could zoom in with 5 times the resolution of Soho's.
It's like somebody gives you glasses after you have been nearsighted for most of your life. We've seen things that nobody has seen, nobody's imagined before. We've learned that everything that happens in the outer atmosphere of the sun is incredibly more dynamic than we had imagined.
As the solar cycle climaxed, TRACE observed brilliant solar flares charging the sun's atmosphere.
The smallest of the flares that we see, that are actually measurable by the instruments that we have at the moment, exceed the Earth's power budget easily. The major flares actually involve a good fraction of the total energy output of the sun, which is enormous.
Now it was possible to witness the birth of a solar flare. TRACE showed clusters of thin threads, loops of the sun's magnetic field. They originated from sunspots on the surface far below. Magnetic imaging systems revealed each sunspot to act like one end of a bar magnet. Sunspots of opposite polarity jostled to pair up. It was the beginning of a solar storm. A new sunspot appeared alongside an existing north-south pair. A colossal burst of activity ensued as magnetic fields reorganized. A solar storm was born.
Sometimes that can happen relatively smoothly, and it just causes the background glow, the actual heating of the corona. Occasionally that triggers a whole cascade of reorganizations that leads to a big flare or a big coronal mass ejection.
Finally, an answer as to why the sun's corona could be so much hotter and more violent than the sun's surface. Energy from deep inside the sun was transported via magnetic field lines. As to what created that energy, scientists agreed: nuclear fusion at the sun's core. But fusion had never been directly observed. Theory has it that when nuclear fusion creates a helium atom, neutrinos are emitted. Trillions of mysterious neutrinos bombard us every second. So small they pass through the Earth as if it were invisible. If they could be measured coming in a trajectory from the sun, and in sufficient quantities, it would prove beyond doubt that fusion fueled the sun's core. Ironically, the first evidence came not from far-flung satellites, but from deep within the mountains of western Japan. Super Kamiokande is one of the most ambitious scientific projects of the century. It was built to capture solar neutrinos. But only one neutrino in 100 billion could be trapped. It called for a remarkable detector. One kilometer underground, an enormous cavern was prepared for filling with the purest water in the world. Its walls were studded with 10,000 light detectors. When a stray neutrino strikes a water molecule, an electron is chipped off. The shock wave creates a tiny flash of light, indicating the direction the neutrino has come from. Super Kamiokande scientists eventually measured neutrinos emanating from the sun. In 1991, they claimed they'd observed the first direct evidence that fusion took place in the sun's core. The only doubt was that the number of neutrinos detected fell far short of predictions.
In our detector, we expect to see something like 30 or 40 events per day, depending on the energy that we are looking at. And we see about 20 events per day. And that's the real crux of the problem, is why are there so few neutrinos that we detect as opposed to what we're predicting from the sun. And many different types of experiments have seen this over the last 30 years. And so there's two possible explanations. One is that the models of the sun, nuclear reactions in the sun, are incorrect, and we think now that that's pretty unlikely. And the other possibility is that something's happening to these neutrinos when they're traveling from the sun to the Earth where we detect them.
Perhaps fewer neutrinos were seen because they alter before they reach the Earth and go undetected. It was a crucial question. If physics of the sun were in doubt, so was our understanding of the entire universe. To their relief, in August 1998, Super Kamiokande scientists discovered that a related particle called a muon neutrino had mass. If neutrinos have mass, they argued, they are capable of splitting into something smaller, a particle that Super Kamiokande was incapable of detecting.
If one of the neutrinos, the muon neutrino, has mass and is transforming as it travels to our detector underground, then it's very likely that the electron neutrinos generated in the core of the sun also have mass. So it's becoming more and more likely that neutrino mass is in fact the explanation for the solar neutrino problem that we have. And of course that's very exciting for reasons of cosmology and particle physics.
With the fusion process confirmed, scientists could reconstruct events at the sun's core. Neutrinos fly from the sun's center at near light speed. Light itself, traveling as photons, struggles to overcome the immense density. It diffuses through 600,000 kilometers of thick gas in the Sun's inner shell. 200,000 kilometers from the surface, it enters a region where the gas is so turbulent it bubbles. A photon takes years to travel from the core to the Sun's surface. From there, it takes a mere 8 minutes to reach planet Earth, where it has sustained human civilization for a mere fraction of the Sun's lifetime.
When we look at biological evolution, which has taken all this time to evolve to us, we shouldn't think of ourselves as the culmination. We are maybe not even the halfway stage, because evolution has far more time ahead of it, even before the Sun dies, than it has had up till now to evolve us. And of course, if we go to the wider universe, it has an infinite future probably ahead of it. So if we put ourselves in this broader context, it makes us seem just a step on the way, and certainly in no sense a culmination.